the next point. We should ensure whatever we see is clear.
That means work is being done. We can see that it is in opposite direction.
Hello and welcome to a wonderful moment again in the Ministry of Education Kaduna State e-learning platform. Today we'll be discussing chemistry and I'll be building on the last topic we had, and our topic for today is mass-volume relationship for a chemical reaction. If you remember, in our last lesson we did see how to balance a chemical reaction. Today we'll be looking at some simple calculations involving stoichiometry. And under this, we'll be looking at the following outlines, as we'll be looking at stoichiometry of a reaction. We'll be looking at IUPAC convention and SI units. We'll be looking at relationship between quantities, and we'll be looking at the application, concentration times, and finally, we'll be looking at the calculation and application of this stoichiometry. Like I said, this aspect is basically calculation. And the stoichiometry of an equation is, stoichiometry of a reaction is the process of measuring chemical element in quantitative relationship in chemical reaction. It is simply the arithmeticals which give the relationship of reactant and product. If you look at our lessons last week, we also saw how you can balance a chemical reactions. And this balancing of chemical reaction has to do on the law of conservation of mass. Today we'll be looking at this stoichiometry. The mass-volume relationship in a chemical reaction is used to determining the stoichiometry of several reactions, such as precipitation, synthesis, and reduction of metallic oxide, analysis of chloride, etc. A stoichiometric equation is a balance equation. Now, we'll look at the concept of a mole. In our last lesson, we did define a mole, but today we will say a mole is the number of particles. The particles may be atoms, ion, molecules, or electron. Like I said in my last lesson, a mole is a unit of measurement. And when you measure quantities with reference to Avogadro's number, and this Avogadro's number is approximately 6.02 times 10 raised to the power of 23 in magnitudes. Now, relationship between quantities. In our previous lesson, we saw other concepts like molar mass. Therefore, the mole is the amount of a substance which contains the same number of specific particles as there are in 12 carbons, as there are in carbon atoms in 12 grams of carbon-12 isotope. The molar mass of an element is the mass of 1 mole of that element, and usually it is measured in grams per mole. Example is 1 mole of sodium atom has 23 grams. 1 mole of sulfur atom has 32 grams, 1 mole of magnesium atom has 24.3 grams, and so on and so forth. So, molar mass of a compound is the mass of 1 mole of a compound. It is the relative formula mass expressed in grams. Remember I said molar mass can also be referred to as formula mass because it is calculated from the accurate formula of a specific compound or a molecule. Now, molar volume of a gas. This is the volume occupied by 1 mole of a gas as standard condition. And these standard conditions of temperature and pressure is called STP. STP stands for standard temperature and pressure. The value for molar volume is 22.4 dm cube, which is the same thing as 22,400 centimeter cube. And the standard temperature is 273 Kelvin. Of course, standard pressure is 1 atmospheric pressure, or 1.01 times 10 raised to the power of 5 newtons per meter square. Now, these are standard quantities I will be making reference to as we progress in our lessons today. My wonderful viewers, listeners at home, as well as my learners, I want to give you the standard abbreviated symbols for certain quantities as well as their SI unit. Remember, SI unit is System International Units that are generally acceptable globally. Now, when we say mass, it is represented by small letter m, and the unit is in grams or kilograms. Molar mass is capital letter M. Remember, for a mole, molecule is molar mass, and for an atom is atomic mass. But they have the same symbol of capital letter M, and the unit is in grams per mole. Remember I said in my last class, if it is relative, there is no unit. Molar volume V is centimeter cube or decimeter cube. Amount, small letter m, is measured in moles. Molar concentration, capital letter C, is measured in moles per dm cube. And our mass concentration, usually measured in P, is grams per dm cube. And of course, our Avogadro's constant L, which is also our Avogadro's number, capital letter M, which is measured in per mole. My wonderful students, I will give you some very, very important formula that we'll be using as we progress in today's lesson. I'd like you to know that amount in mole is measured in mass in grams over molar mass in grams per mole. I'll take it again. Amount in moles is calculated by mass in grams all over molar mass in grams per mole. As you can see, representing the symbol, small letter N is amount, small letter M is mass, and capital letter M is molar mass or atomic mass, as the case may be. Now look at the other one, which is number of particles. Remember we say when we say particles, we are talking about molecules, atoms, ions, electrons, just to mention but a few. So when you are calculating number of particles, the formula is amount in moles times Avogadro's constant. As always, except otherwise, Avogadro's constant is 6.02 times 10 raised to the power of 23. And we say Avogadro's constant is calculated as number of particles all over amount. It's just a play on that formula we mentioned earlier on. When you make subject of formula, you arrive at our Avogadro's constants. Now, how do we get our molar volume? Our molar volume is gotten by a molar volume equals to volume over amount. We'll be using some of these formulas that we have mentioned earlier to see how we can manipulate them to get answers when we are approached by certain problems. Now we'll be looking at concentration terms, which is the next aspect that we'll be seeing shortly, where we'll be looking at molar concentration. And we say molar concentration is the amount in moles over volume in centimeter cube multiplied by 1000. The 1000 usually is to convert from centimeter cube to decimeter cube. So if we say C is equals to M over V, we'll have converted the centimeter cube to decimeter cube. The V there is in decimeter cube. The mass concentration is mass in grams over volume in centimeter cube times 1000. Now there's a relationship that connects mass concentration, molar concentration, and molar mass. And the relationship is mass concentration is equal to molar concentration times molar mass. And we have this relationship that says concentration is proportional to number of moles. So we say Ca Va over Cb Vb is equals to Na over Nb. All these and many more I've mentioned earlier on. We're going to apply them and see how you can use them to solve problems when you are confronted with a question in an exam or otherwise. So we'll look at example number 1. Our example number 1 will be coming up as we'll be looking at the question. It says, calculate the mass of sodium chloride required to completely react with 85.0 grams of silver trioxynitrate 5. And we say silver is 108, sodium is 23, and chlorine is 35.5. Let's go to the solution. First and foremost, you must show us the stoichiometry, which is the equation of the reaction. And you can see there sodium chloride reacting with silver trioxynitrate 5 to give you silver chloride plus sodium trioxynitrate 5. The mole ratio of both reactant and product is 1:1:1:1, meaning that 1 mole of sodium chloride reacted with 1 mole of silver trioxynitrate 5 to give you 1 mole of silver chloride and 1 mole of sodium trioxynitrate 5. So you can relate 1 mole to 1 mole since they are the same ratio. And that's why we say 1 mole of sodium chloride will react with 1 mole of silver trioxynitrate 5. And since the information that is given to us about silver trioxynitrate 5 as 85 grams, we will calculate the number of moles, which is mass over molar mass. And if you calculate the molar mass of silver triagonite 5, it will give us 108 plus 14 for nitrogen plus 16 times 3 because there are 3 oxygens there. And our value ultimately will be 170 grams per mole. So if you substitute the mass, which is 85.0 grams, and divide by 170 grams per mole, you find out that it's 0.50 moles of silver trioxonitrate 5. Remember that if 1 mole of sodium chloride reacts completely with 1 mole of silver trioxonitrate 5, it therefore means that 0.5 mole of sodium chloride will completely react with 0.5 mole of silver trioxonitrate 5. So you make reference, and if you are making reference, you now say mass of sodium chloride is equals to amount of sodium chloride times molar mass. And the molar mass of sodium chloride is sodium is 23 plus chlorine, which is 35.5, which gives you 58.5 grams per mole. So to get the mass, you just say 0.5 mole, which is number of mole of sodium chloride, times 58.5 grams, which will give you 29.25 grams, which is the answer. But there are alternative means of doing this. Alternatively, if you are not happy with my first solution, you could go directly and say 58.5 grams of sodium chloride, which is the molar mass or the mass of 1 mole of sodium chloride, will react completely with 170 grams of silver triagonite 5, which is the molar mass of 1 mole of silver triagonite 5. Then you ask, what mass, which is S gram of sodium chloride, will react completely with 85.0 grams of sodium triagonite 5. The rest is arithmetic or mathematics. You make X the subject of the formula, and you have it to be S grams is equals to 58.5 grams of sodium chloride times 85 grams of sodium triagonite 5 all over 170 grams of silver triagonite 5. Obviously, the silver triagonite 5 will cancel out, the grams will cancel out. What will be left out there is sodium chloride. So if you do the division with your calculator, you arrive at 29.25 grams of sodium chloride, which is similar to the answer we got earlier. But of course, you must always know that your S grams represent mass of sodium chloride. That's the solution. I've given you 2 options to choose from. Anyone you are more familiar with, I'm sure you can lay your hands on it when the problem comes up. The next question is, in an experiment, which zinc was reacted with copper 2 tetrasulfate 6 solution, the mass of zinc used was 0.46 grams, and the mass of copper displaced was 0.45 grams. Now calculate 1 mole of zinc atom used, 2 mole of copper atom displaced. You are given information that zinc is 65 and copper is 63.5. Now, if you look at what we have said earlier, stoichiometry is just how to write a balanced equation. My wonderful students, looking at the solution, we'll be looking at calculating the number of mole of zinc. Remember in my formula I said number of mole is mass in grams over molar mass. From our question, we are given that 0.46 grams of zinc, and the molar mass or atomic mass of zinc, as the case might be, is 65 grams per mole. So if you do your division and punch your calculator, you arrive at 0.007077, approximately 0.00708 moles of zinc. Now, in the same question, you were asked to calculate the number of mole of copper that was displaced. So if you look at it also, you find out that number of mole of copper displaced is equals to mass in grams over molar mass in grams per mole. And from our question, the mass of copper was 0.450 grams. And the atomic mass or molar mass of copper is 63.5 as given in our question. So like as usual, when you punch your calculators, you arrive at 0.00709 moles. Now let's look at the relationship between these 2 substances that we are involved in a chemical reaction. Now you can see that after we have calculated the number of mole of both zinc and copper, we are able to arrive at 0.000708 and 0.000709. Now looking for the ratio, we'll divide through by the lowest of the 2 values, which of course is 0.00708. So if we say 0.00708 divided by 0.00708, and we say 0.0079 divided by 0.00708, we obviously arrive at the answer 1:1. And by implication, it means that 1 mole of zinc displaces 1 mole of copper. Now, if we are to write it theoretically, you look at the equation there. Zinc reacting with copper 2 tetraosulfate 6. And zinc displaces copper in the reaction. You can see it there. And the balance equation is such that 1 mole of zinc reacted with 1 mole of copper 2 tetraosulfate 6 to give you 1 mole of zinc tetraosulfate 6 and 1 mole of copper displaced. It means that our calculation have agreed with the equation as written below. Now, let's take the next example. It says, what is the amount in mole of hydrogen gas that will be produced if 6 mole of hydrochloric acid react with SX zinc, and calculate the volume of hydrogen gas involved at STP? This question was lifted from WAEC 1995 May-June. Now let's look at what the solution will look like. First of all, you must give us a stoichiometric equation. Like I said, a stoichiometric equation is a balanced equation. Looking at it there, we see zinc will react with 2 mole of hydrochloric acid to give you zinc chloride, and hydrogen gas will be liberated. Now from the mole ratio, you find out that 1 mole of zinc reacts with 2 mole of hydrochloric acid to produce 1 mole of zinc chloride and 1 mole of hydrogen gas. Now, so from the equation, 2 mole of hydrochloric acid produce 1 mole of hydrogen gas, as you can see illustrated on the equation. So, if 2 mole of hydrochloric acid react with 1 mole of hydrogen gas, then 0.6 mole of hydrochloric acid will produce X, which is unknown mole of hydrogen gas. If you do the proportionality, as we do it in mathematics, you will resolve that X mole of hydrogen gas times 2 mole of hydrochloric acid is equal to 0.6 mole of hydrochloric acid times 1 mole of hydrogen gas by cross multiplying. Making X the subject of the formula, we will say X mole of hydrogen gas equal to 0.6 mole of hydrochloric acid times 1 mole of hydrogen gas divided by 2 mole of hydrochloric acid. And our final answer after punching our calculators will be 0.30 mole of hydrogen gas. Now look at it. It says volume of hydrogen gas liberated at STP. Remember that I said at the earlier stage of this lesson that 1 mole of any gas at STP will occupy a volume of 22.4 dm cube or 22,400 centimeter cube. So if you relate it to what we have today, we will say 1 mole of hydrogen gas occupies 22.4 dm cube at STP. 0.30 mole of hydrogen gas will occupy an unknown volume. And that unknown volume will be obtained by saying 0.30 moles multiplied by 22.4 dm cube. And your final answer will be 6.72 dm cube of hydrogen gas will be liberated at STP. My wonderful viewers at home, like I said earlier on, sometimes you'll be given an isotopic mixture with different relative abundance in the atmosphere. And you'll be asked to calculate the relative atomic mass or the mean atomic mass. Now, there are 2 ways to go about it, which I will take through as we round up today's lesson. Remember, I said this lesson is coming in 2 series. So watch out for the next series where I will be doing more examples, and I'm sure it will help you as you understand these concepts better. Now, the question says, X is an element which exists as an isotopic mixture containing 90% of 39 and 10% of 41. meaning that they are isotope having the same atomic mass but different, the same atomic number but different atomic masses. So if you look at this isotopic mixture, you find out that X has atomic mass of 39 but atomic number of 19, and the other has atomic mass of 41, atomic number of 19. Remember that the first one is 90% in abundance in the atmosphere, while the second one is 10% in abundance in the atmosphere. So to calculate the mean relative atomic mass of X, we will say 90%, that's 90 over 100, times 39, then plus 10 times 10 over 100 times 41. Remember, 41 is the atomic mass of the second one, and 39 is the atomic mass of the first one. If you resolve this mathematically, you will have 3,510 plus 4,101 divided by 100, and the final value will be 39.2. So the mean atomic mass, or the mean relative atomic mass of that sample X, which is an isotopic mixture, is 39.2. Like I said, it's always done two ways. Choose the one that suits you more. So alternatively, we can say find the ratio of the percentages. Remember, the first percentage is 90% and the second percentage is 10%. And like I said, in finding ratio, you divide through by the lowest value. Between 90 and 10, obviously 10 is the lowest value. And that's why we say 90 divided by 10 and 10 divided by 10. You will get 9:1. So what do? You multiply the atomic mass corresponding to the ratio. The first atomic mass is 39 times 9. It gives you 351. While the second one is 41 times 1. It gives you 41. So if you put 351 plus 41, you will get 392. And what is the sum of the ratios? The sum of the ratio is 9 plus 1, which gives you 10. So if you divide the sum of the atomic masses multiplied by their ratios by 10, you will get 39.2, which is the same as the first alternative that we took. My wonderful student, in chemistry, there are many ways of going through the answers. Of course, you must know that what you are doing must be in accordance with certain rules and guidelines in chemistry. As I round up today, I hope that you can visit any of these materials to get more knowledge on the subject matter. Remember, I'm always your chemistry teacher. My name is Philip Mamman. You can always contact me if you have issues, or you want to submit your assignment, or you want to verify or make contribution on the number 080-2659-8861. I'll take it again. Philip Mamman, 080-2659-8861. My other colleague, Ibrahim Umar, you can find him on 070-3620-2842. Ibrahim Umar again, 070-3620-2842. And finally, Mr. Williams Ishaku, you can also contact him at 081-6067-0920. Williams Ishaku, 081-6067-0920. My wonderful students, come to the end of today's lesson. Remember, I say you should watch out for the next lesson. That will be a continuation of this topic, where I will be looking at more examples and more exposition. Do have yourself a wonderful time. Stay safe, stay at home, keep learning. Coronavirus is real. My name is Philip Mamman once again. Have a beautiful day.